Large Hadron Collider is one of the wonders of the modern world. It's believed to be the largest and most complex machine mankind has ever created. Buried hundreds of feet beneath Switzerland and France,
in the heart of Switzerland, nestled among the rolling hills and beautiful landscapes, lies CERN, the European Council for Nuclear Research.
Each slice was brought through from there, from that hole up there, 100 meters, and installed here.
Known for its groundbreaking experiments and cutting-edge technology, CERN has long been at the forefront of scientific exploration. But behind the facade of innovation and discovery lurks a tale of darkness and fear. What shocking discovery was made at CERN? And why are renowned scientists terrified? Join us as we uncover Switzerland's terrifying discovery at CERN before shutting it down. Exploring the depths of modern physics. As an international organization funded by 23 member states, the primary mission of the European Council for Nuclear Research, CERN, is to delve into particle physics and propel scientific understanding forward. The latest installment, Round 3 of the Large Hadron Collider, marks a new phase in their quest for discovery. The Large Hadron Collider, also known as the LHC, began its operations in 2008, sparking intense debates and discussions worldwide. While some scientists envisioned ambitious experiments, others raised concerns about potential dangers to humanity. How exactly does the LHC function? Situated underground near the border of France and Switzerland, the LHC takes the form of a ring-shaped tunnel with a circumference spanning an impressive 27 kilometers, equivalent to roughly 16.7 miles. Within this tunnel, two vacuum pipes are laid out, intersecting at various points. A network of 1,232 main magnets runs through these pipes, tasked with the mission of accelerating protons to velocities nearing the speed of light, while ensuring that the particle beams remain on course and avoid collisions with the tunnel walls. To power these magnets, superconductive cables stretching over a staggering total length of 250,000 kilometers, or approximately 150,000 miles, are employed. To put this into perspective, if scientists were to dismantle the LHC and unwind these cables, they could encircle the Earth around 6 times at the equator. Even after such an endeavor, there would still be an abundance of wire left over, enough to construct a power grid in Antarctica. Although the notion of a power grid in Antarctica might seem odd, it underscores the sheer magnitude of resources involved in powering the LHC's operations and the potential for repurposing them for other ambitious projects. It's fascinating to think of the LHC as the grandest refrigerator ever conceived. For the LHC's magnets to function flawlessly, they need to be chilled to a bone-chilling temperature of -271.3 degrees Celsius, colder than the vast expanse of space itself. Achieving such frigidity requires a staggering 120 tons of liquid helium to be poured into the LHC. Now, consider the humble refrigerator in your kitchen. Inside, special substances called refrigerants work their magic to keep your food cool. Liquid helium is one such refrigerant, but on a vastly larger scale within the LHC. In your household refrigerator, you might find about 30 to 50 grams of refrigerants. Comparatively, the LHC eclipses this by approximately 4 million refrigerators worth of coolant. But instead of chilling groceries, it's dedicated to unraveling the most complex mysteries of modern physics. Consider, for instance, what exactly makes up matter. Back in school, we learned that matter is composed of molecules, which in turn are made up of atoms. These atoms consist of even smaller particles known as protons, electrons, and neutrons. But what's truly fascinating is delving deeper into the complex world of these tiny building blocks that form everything around us. Modern science has delved deeper into the mysteries of the universe. Take, for instance, the tiniest building blocks of an atom, like protons. Scientists discovered that protons aren't the smallest entities. They're made up of even tinier particles called quarks. To grasp their minuteness, imagine an atom ballooning to the size of our planet Earth. In this scenario, a proton would stretch out to about the length of a football field. Now, think about the quark within that proton. It would be just about the size of a couple of inches, small enough to snugly fit in your pocket. But how do we even observe something so tiny? That's where the LHC comes into play, designed to unravel the secrets of these subatomic particles. Imagine two streams of protons racing in opposite directions, gathering speed until they slam into each other head-on. It's like stacking bricks. When you drop one on top of the other, bits and pieces scatter in all directions. Similarly, when protons collide, tiny fragments can break free. But here's the catch. To witness this cosmic crash, we need a special machine called a collider. Think of it as a giant microscope for the subatomic world. Yet getting those protons to collide is no easy feat. They have to meet dead center, which is no small task. Plus, these particles are invisible to the naked eye, so physicists rely on the trails they leave behind to study them. Unraveling the cosmic puzzle. The LHC isn't just a particle crash course, it's a quest for the unknown. One of the remarkable achievements of the LHC is its ability to question the standard model of particle physics. This model, developed over decades by scientists around the world, describes three of the four fundamental forces in the universe: electromagnetic, weak, and strong interactions, leaving out gravity. Imagine you're trying to solve a puzzle, and the standard model helps you put together many pieces. The standard model is like a cosmic rulebook, guiding the interactions between particles, like those making up protons and neutrons. Within this model you have quarks, leptons, and bosons, each with its own role to play. Quarks, for instance, are like the tiny, vibrant Lego bricks of the universe. But they come in 6 different types, each with its own charge and mass. Leptons, on the other hand, are like the graceful dancers of the particle world, including electrons, muons, and tau particles. They don't feel the strong nuclear force, but they're crucial for the dance of atoms. Then there are the bosons, which are like the messengers carrying the news of forces between particles. You've got photons, spreading the word of electromagnetism, W and Z bosons, doing the heavy lifting for weak nuclear forces, and gluons, the glue that holds quarks together with the strong nuclear force. Now, while the standard model does a pretty good job of predicting what happens in physics experiments, it's not flawless. That's where the LHC steps in. The LHC zooms in on the tiniest particles and their interactions. Take the beauty quark, for example. According to the standard model's predictions, when beauty quarks decay, they should do so into muons and electrons at similar rates. But when scientists looked closely at the data from the LHC, they noticed something odd. The decay wasn't following the rulebook. This anomaly suggests there might be some mysterious particles or forces at play that we haven't discovered yet. But there's more. Sometimes, when particles collide in the LHC, they create entirely new particles that leave scientists scratching their heads. Like the pentaquark, a particle with not 3, but 5 quarks. It's like finding a new flavor of ice cream you never knew existed. This discovery has sparked a lot of excitement because it challenges our understanding of how particles are put together. So, in a nutshell, while the standard model gives us a solid foundation, the LHC is like a treasure trove of surprises, revealing the hidden secrets of the universe one collision at a time. This discovery opened up a whole new avenue for understanding matter, suggesting that there might be a hidden force at play in the subatomic realm, one that scientists are still puzzling over. The statistical significance of finding the pentaquark was staggering, with a deviation of 15, showcasing the remarkable precision and capability of the LHC. In particle physics, a discovery typically needs a deviation of at least 5 standard deviations to be considered solid, so a whopping 15 deviations practically shouts that this wasn't just a lucky break. But that's not all. The LHC had another trick up its sleeve with the discovery of the tetraquark, adding yet another layer to the particle puzzle. This exotic particle, known as TCC+, is like the 4-leaf clover of quarks, consisting of 2 charm quarks and 2 lighter ones, all bound together by the strong nuclear force. The discovery of the tetraquark was a triumph for the LHCb detector, which caught a glimpse of the TCC+ signature amidst the chaotic aftermath of proton collisions. It was like finding a needle in a haystack, especially considering that the TCC+ exists fleetingly before transforming into other particles. Yet despite the challenges, the LHCb team managed to capture this elusive particle, adding another gem to the treasure trove of particle physics discoveries. This finding not only expanded our understanding of quark combinations, but also holds the promise of shedding light on the complex world of quantum chromodynamics, QCD. QCD is like the grand master of the particle world, governing how quarks interact under extreme conditions. It's a crucial piece of the standard model puzzle, but also one of the most intricate and challenging aspects of particle physics. Understanding QCD is like unlocking the secrets of how quarks dance when the music gets intense. New frontiers in particle physics. It was through the LHC's lens that scientists stumbled upon the elusive Higgs boson, a particle so vital it's dubbed the cornerstone of the cosmos. Why is it so crucial? Well, imagine it as the glue that holds everything together. Without it, all other particles, and consequently all matter, would lose their weight and zip through space at light speed. But the LHC's mission doesn't stop there. It's like a magnifying glass for the tiniest building blocks of the universe. These particles, too small to see with the naked eye, play crucial roles in the dance of atoms. And the only way to catch a glimpse of them is when protons do their collision dance. That's when special detectors swoop in to catch these fleeting particles, offering glimpses into the hidden world of the infinitesimally small. Following the completion of additional experiments and the accumulation of more data at the LHC, scientists redirected their focus toward delving deeper into the intricacies of the Higgs boson. Through meticulous analysis of collision data gathered by the LHC, researchers made a remarkable revelation. The Higgs boson may possess a greater mass than previously believed, exceeding 125 giga-electron-volts per speed of light squared. The significance of this newfound mass measurement cannot be overstated, as it has sparked considerable debate and controversy within the scientific community. If indeed the Higgs boson proves to be heavier than anticipated, it would necessitate a fundamental reassessment of our comprehension of the fundamental constituents of the universe. Such a discrepancy could signal the existence of particles and forces beyond the purview of the standard model of particle physics, ushering in a new era of exploration in physics. Moreover, the anomalies observed in the behavior of beauty quarks suggest the potential influence of yet undiscovered particles or forces, further complicating the current understanding of particle physics. The prospect of revising or replacing the standard model looms on the horizon, challenging physicists to venture into uncharted territory in search of a more comprehensive framework to explain the mysteries of the cosmos. Additionally, the revelation of a heavier Higgs boson has reignited interest in exploring the intricate dynamics of the Higgs field and its role in shaping the fabric of the universe. Dark matter exploration at the LHC. The groundbreaking discovery of the Higgs boson at the Large Hadron Collider marked the culmination of years of tireless effort and collaboration among countless brilliant minds. It served as the final puzzle piece needed to validate the standard model of particle physics in its current form. However, despite this milestone achievement, numerous profound questions remain unanswered, particularly regarding the mysterious nature of dark matter. Contrary to what was once believed, the revelation of the Higgs boson did not signify the conclusion of particle physics, but rather ushered in a new era of exploration. Many physicists speculate that unraveling the mysteries of elusive dark matter may hold the key to furthering our understanding of the universe. While its existence is evident, its composition remains a profound puzzle. It is theorized to be a new type of particle or perhaps an entire family of particles that interact solely amongst themselves, evading detection by traditional means. To detect such elusive particles, scientists employ various methods, each represented by different Feynman diagrams depicting particle interactions. One approach involves direct detection experiments, where dark matter particles scatter off standard model particles, such as quarks or electrons, within a detector. These experiments offer a glimpse into the elusive realm of dark matter, shedding light on one of the universe's most captivating mysteries. Certainly, these types of interactions between dark matter and regular matter are exceedingly rare, or else we would have already detected dark matter. However, given a sufficient number of particles and ample time, we should eventually observe an interaction between a dark matter particle and a regular matter particle. To detect dark matter, scientists have devised large containers filled with liquid or massive crystals, strategically positioned deep underground to shield them from cosmic rays. Despite our efforts, we have yet to observe a single collision that aligns with the dark matter particle hypothesis. It's possible that our detectors are not large enough, or perhaps we simply haven't waited long enough for these rare interactions to occur. Another approach, known as indirect detection, involves a different perspective represented by rotating our Feynman diagram. These diagrams, which depict particle interactions in space and time, offer multiple orientations, each revealing unique insights. In this case, the orientation shows the elimination of a particle-antiparticle pair from the dark sector, resulting in the creation of a known particle-antiparticle pair. For instance, two dark matter particles elsewhere in space could collide, producing gamma-ray photons that might be captured by telescopes like the alpha magnetic spectrometer. Detecting excess gamma radiation from high-density regions of our galaxy could indicate dark matter annihilations. However, distinguishing this gamma-ray source from other astrophysical phenomena, such as pulsars, supernovae, or black hole activity, presents a significant challenge. So far, despite our efforts, we have not obtained clear evidence using this method. Let's give our Feynman diagram another spin and explore a new perspective. Now, instead of dark matter particle destruction, let's consider dark matter being created from the destruction of some standard model particles. Some theorists propose that we could observe this phenomenon by examining the high-energy collisions of standard model particles in collider experiments like the LHC. This is where the Higgs boson re-enters the picture. At the LHC, particles of regular matter collide, such as protons or heavier nuclei, generating a plethora of exotic particles in the process. These particles are either detected directly when they collide with detectors surrounding the collision point, or they decay into other particles due to their inherent instability. Among all the particles produced in these collisions, scientists believe that the elusive Higgs boson has the highest likelihood of producing a dark matter particle. But why is that? Firstly, particles with electrical charge or color charge cannot decay into Higgs bosons because the Higgs itself lacks such charges. If it did possess them, we would have detected it through its interaction with electromagnetism and the strong force already. Therefore, electrically charged leptons, like electrons, muons, and tau particles, as well as quarks and their composites, are excluded from consideration. Additionally, the W boson of the weak nuclear force and the color-charged gluons of the strong nuclear force are also excluded. Furthermore, photons are excluded from consideration because dark matter's defining characteristic is its lack of interaction with light. With these exclusions, there are very few candidates left within the standard model. Exploring extra dimensions. Imagine a universe beyond what we perceive, a realm where dimensions stretch beyond our familiar three. This is the essence of the theory of extra dimensions, a concept that extends our understanding of space in ways we've never imagined. Picture dimensions beyond length, height, and width, intertwined with the fabric of our universe, yet hidden from our everyday perception. These additional dimensions might exist in minuscule scales, curled up or compressed to the point of invisibility to our current technology. It's similar to observing a rope from a distance. What appears as a one-dimensional line gradually reveals its thickness and curvature upon closer inspection. Similarly, these extra dimensions may envelop us, yet elude our detection. But why delve into dimensions beyond our three-dimensional world? The quest lies in unifying the fundamental forces of nature, particularly the elusive force of gravity. While the standard model comprehensively describes three fundamental forces, electromagnetism, strong nuclear force, and weak nuclear force, gravity remains a puzzle. It's notably weaker compared to the other forces, a disparity that has baffled scientists for centuries. Interestingly, the theory of extra dimensions proposes that gravity's weakness stems from its dispersion into these unseen dimensions. Here's where the LHC steps in as a vital tool for exploration. With its unparalleled precision in probing the subatomic realm, the LHC unravels mysteries that defy the standard model. From unexpected particle collisions to the peculiar behaviors of quarks, the anomalies detected by the LHC hint at phenomena beyond our current understanding, phenomena that the theory of extra dimensions could potentially illuminate. If we ponder the Higgs boson particle, which appears to weigh more than we thought at first, it could be mingling with mysterious particles or fields from these extra dimensions. These hidden dimensions might explain why the Higgs boson seems heavier than expected. Similarly, the puzzlingly quick decay of beauty quarks might be influenced by forces or particles from these unexplored realms of extra dimensions. Moreover, the theory of extra dimensions holds significant implications for the validation of fundamental theories like string theory. According to string theory, particles are not infinitesimal points, but rather tiny vibrating strings. These strings are believed to exist in multiple dimensions, with their vibrations in 10 dimensions, generating the particles and forces observed in our universe. Thus, the existence of extra dimensions is crucial for the validity of string theory, adding another layer of intrigue to the exploration of these hidden dimensions. How do scientists utilize the LHC to uncover the potential existence of extra dimensions? One crucial aspect is the capability to observe particle behavior at incredibly high energy levels. When particles collide at such energy levels, they disintegrate into their fundamental constituents, revealing the underlying fundamental forces and their interactions. Therefore, the patterns of interaction and decay of these particles play a pivotal role in the search for extra dimensions. Imagine we've successfully collided particles, resulting in a cascade of subatomic particles. If we confine our analysis to the known ions, the energy and momentum from this collision will only be attributed to the particles familiar to us. However, if extra dimensions indeed exist, there's a possibility that this energy and momentum could extend into them. Scientists are keenly looking out for this phenomenon because any unaccounted for energy and momentum could indicate the presence of these additional dimensions. Certainly, these experiments demand extreme precision, necessitating detectors of remarkable sophistication to discern even the slightest anomalies. Another avenue scientists explore to elucidate the presence of extra dimensions is through the analysis of decay patterns. When certain particles undergo decay, they transform into other particles in predictable ways, governed by the laws of the Standard Model. However, deviations from these anticipated patterns may occur if unknown extra dimensions are at play. Therefore, scientists carefully scrutinize the decay patterns of these particles, remaining vigilant for any deviations that could indicate the influence of extra dimensions. Now it's time for today's subscriber pick. In the shadowy depths of CERN, where secrets intertwine with the fabric of reality, Switzerland made a chilling discovery that sent shockwaves through the scientific community. It all began with a routine experiment, a quest for knowledge amidst the whirring of particle accelerators. As the proton beams collided with unprecedented energy, a rift in the fabric of space-time materialized before the astonished eyes of the researchers. Out of the abyss emerged a creature, its form elegant yet unmistakably terrifying. With eyes ablaze with otherworldly knowledge, it spoke in a tongue unknown to humankind. Its presence filled the halls of CERN with a deafening silence, freezing the blood of those who beheld it. As fear gripped the hearts of the scientists, Switzerland made the unprecedented decision to shut down CERN, sealing its doors to the outside world. Rumors swirled among the populace, whispers of a portal to the unknown, of dark forces unleashed by the hubris of humanity. Yet, despite the closure, the news of Switzerland's terrifying discovery at CERN, before shutting it down, lingered, a haunting reminder of the thin veil between discovery and destruction. As the world pondered the fate of CERN, one question remained unanswered. What other horrors lay dormant in the depths of CERN's mysterious facility? CERN's enduring quests. Apart from the obvious task of accurately understanding the new particle, scientists are delving deeper into the mysteries of the Higgs boson for two primary reasons. Firstly, they aim to uncover the origins of the physical vacuum that has enveloped our universe since its early beginnings. Secondly, they seek to comprehend how this physical vacuum can remain stable over time. The Higgs field plays a crucial role in this puzzle by imparting non-zero potential energy to the physical vacuum. a phenomenon that significantly impacts the workings of our cosmos. Researchers believe that unraveling the nature of this energy potential holds the key to understanding fundamental forces like electromagnetism and weak nuclear force. To achieve this, scientists are investigating the interactions between Higgs bosons, necessitating the creation of pairs of these elusive particles. While the discovery of the Higgs boson has shed light on how other particles acquire mass, its own mass remains unexplained. The absence of symmetry in existing theories poses a challenge, potentially leading to instability and disruption of the physical vacuum due to quantum fluctuations. Although such disruptions occur on timescales far beyond the known lifespan of the universe, scientists are actively searching for additional Higgs boson-like particles that could signal the presence of new physics necessary to stabilize the mass of the Higgs boson. All these factors underscore the importance of delving into significantly more data and, if possible, accessing higher collider energy levels. This is why, even a decade after the discovery of the Higgs boson, hundreds of experts worldwide remain dedicated to this endeavor. The journey to discover the Higgs boson, proposed in 1964 and found in 2012, has raised questions among science enthusiasts about why it took so long. The answer lies in the unique characteristics of the Higgs boson. It's both massive and highly unstable. Creating such a massive particle necessitated the concentration of a vast amount of energy in a confined space, requiring a high-energy collider like the LHC. However, once formed, Higgs particles quickly decay in various ways, with only a small fraction detectable amidst background noise. To capture these elusive particles, scientists constructed the largest and most intricate detectors ever built. They then meticulously analyzed hundreds of billions of proton-proton collisions, searching for the distinctive signature of the Higgs boson amidst the vast sea of data. However, will CERN's endeavors lead to groundbreaking discoveries or catastrophic consequences? Conspiracy theorists have put forth three main hypotheses regarding CERN's activities. The first and most alarming notion is that CERN is striving to open a gateway to the underworld. Some fear that the organization's experiments with subatomic particles traveling at incredible speeds could breach the boundaries between our world and the netherworld. Nevertheless, CERN has clarified that its objective in generating antimatter is to deepen our understanding of matter and mass. Antimatter, particles with the opposite electrical charge of ordinary matter, is believed to have been created during the universe's inception, according to supporters of the Big Bang theory, but it remains exceptionally rare. The second conspiracy theory surrounding CERN revolves around the Mandela effect, a phenomenon where many individuals remember past events differently from reality. Some theorists speculate that CERN's particle experiments could disrupt our reality, potentially propelling our planet into an alternate dimension and triggering widespread instances of the Mandela effect. Lastly, certain conspiracy theorists allege that human sacrifices occur within the premises of the CERN facility. A purported video leaked online in 2016 claimed to show ritualistic sacrifices taking place at CERN, depicting hooded figures conducting a disturbing ceremony. However, a CERN spokesman dismissed the footage as a staged prank. It comes as no surprise that CERN has long been a focal point for conspiracy theories. Thus, when scientists resumed operations on July 5, 2022, following 3 years of enhancements and maintenance, it inevitably sparked renewed speculation online. Despite the disappointment of some scientific enthusiasts, it is evident that CERN harbors no intentions of constructing portals to hell or the future. Instead, within the depths of the world's largest particle accelerator, proton beams continue to circulate around the 27-kilometer circumference, probing the mysteries of physics. Discovering high-energy neutrinos. One of CERN's forward-looking experiments, the LHC's FAIR detector, recently achieved a significant breakthrough. For the first time, it detected high-energy neutrinos generated by a particle collider, identifying 153 neutrino interactions with exceptional precision. This milestone holds great promise for particle physics, offering insights into the universe's most energetic neutrino interactions and shedding light on the mechanisms behind stellar phenomena like supernovae. Neutrinos, tiny subatomic particles present everywhere in the cosmos, are produced through various processes such as nuclear reactions, cosmic rays, and radioactive decay. Despite their abundance, Neutrinos are notoriously elusive, rarely interacting with matter. Every second, trillions of neutrinos pass through every square centimeter of our bodies, yet their ghostly nature renders them imperceptible to human senses. Dubbed ghost particles due to their elusive nature, neutrinos have captured the fascination of scientists since their first detection in 1956, emerging from nuclear reactor-like specters in the night. It wasn't until 2021 that physicists stumbled upon traces of 6 neutrinos, but it took an additional 2 years of meticulous gathering of evidence to confirm their existence beyond doubt. James Boyd, a particle physicist at CERN and co-spokesperson for FAIR, emphasizes the unique potential of these ghostly entities in unraveling the mysteries of deep space. The ultra-high-energy neutrinos detected at the LHC offer invaluable insights into particle astrophysics, offering a window into realms of the cosmos that traditional methods cannot reach. With the FAIR project set to continue its data collection efforts until the conclusion of 2025, scientists are poised on the edge of their seats, eagerly anticipating the discovery of more of these enigmatic ghost neutrinos. Each new revelation promises to unveil yet-to-be-explored realms of physics, leaving scientists eagerly awaiting CERN's next breakthroughs and pondering the implications for the future of scientific inquiry. Do you think that CERN could open a portal to another dimension? Let us know your opinion in the comments below.